All right, so let's talk about using the dot product to find the angle between two vectors. All right, so when two non-zero vectors are placed in standard position, whether in 2 dimensions or 3 dimensions, they form an angle between them. Remember that standard position means that they have our initial point at the origin. All right, so when they have that angle between them, as we see in this figure, the dot product provides a way to find the measure of this angle. So this property is a result of the fact that we can express the dot product in terms of cosine of the angle formed by the two vectors. So let's discuss this theorem that we have available to us then, and the proof that goes along with it. All right, so this is theorem 2.4, evaluating a dot product. All right, so the dot product of two vectors is the product of the magnitude of each of the vectors and the cosine of the angle between them. So just to put it really, really simply for you, the rule is that the dot product, now we know the definition of the dot product is that calculation involving the sum of the product of the components, but it turns out, coincidentally, that value will also give us the magnitude of u times the magnitude of v times cosine of the angle between them. All right, so how do we know this is true? Who came up with this rule? What makes it possible? So here's our proof. For this, we're going to use our vectors u and v in standard position, and we're going to consider the vector that takes one terminal point to the other terminal point, which is our vector v minus u. So we'll place v and u in standard position and consider the vector v minus u, which is not in standard position. We've moved it to that terminal angle. So I'm going to go ahead and include this diagram in my notes. All right, so recall from trigonometry that the law of cosine describes the relationship among the side lengths of a triangle and the angle theta. So this is just kind of a little bit of a recall. So the law of cosines, if this was A, B, and C, the law of cosines says that a squared plus b squared minus 2ab cosine of angle is equal to c squared. So this is a little bit of where Pythagorean theorem comes from, because when we have Pythagorean theorem, we're discussing a right triangle, and cosine of a right angle is 0. So this term would cancel out, giving us a squared plus b squared equals c squared. So there's just a variation of it based on having a different angle. So we're going to use this to prove this relationship between the dot product and these angles. So let's give it a shot. Okay, so by the law of cosines, doing a substitution, we have then that c squared, which is the magnitude of v minus u, quantity squared, is equal to a squared, which is the magnitude of v squared, plus b squared, which is the magnitude of u squared, minus 2 times the magnitude of A, sorry, the A, which is the magnitude of V, times B, which is the magnitude of U. Goodness gracious. V times cosine of the angle between them. So based on all the properties that we talked about before, we can also say that the magnitude of this vector squared, we know, is equal to that vector dotted with itself. And because of the distributive property involving scalars and sums of vectors, we can distribute this expression. So here's how we're going to do the distribution. I'm going to distribute the v minus u into the second set of parentheses, giving us v minus u dotted with v minus v minus with u dotted with u. So I've also taken advantage of the fact that scalars can be pulled out, right? Then I'll do that distribution once more, this time from the right-hand side, distributing the v in this way and the u in this way. Okay, so this is going to give us v dotted with v, minus v dotted with u, or rather, since the u is first, right, we can't take advantage of our commutative property just yet. Then we will distribute this u in to get minus v dotted with u, and then we distribute the u to the u to get plus u dotted with u. All right, so this is by our distributive and associative properties. Then I'm going to take advantage of my commutative property. So the commutative property says that I can swap the order of these expressions. Right? So I'm going to get v dotted with v minus u dotted with v minus u dotted with v plus u dotted with u. All right, so we're taking this very, very slowly, one single step at a time. Bear with me. Remember our property of magnitudes, right? So that's going to say that this is the magnitude of v squared, and this is the magnitude of u squared. And then we can also combine like terms. So we get that this is equal to the magnitude of v squared minus 2 u dotted with v plus the magnitude of u squared. All right, so let's go back. This whole expression equals this whole expression. Okay, so let's put it together. Now, on the left-hand side, we have the magnitude of the difference of v minus u squared. So that we said was equal to this expression down here at the bottom. So the magnitude of v squared minus 2u dotted with v plus the magnitude of u quantity squared is equal to what's on the right-hand side was way up top here. That gives us the magnitude of v squared plus the magnitude of u squared, minus 2 times the magnitude of v times the magnitude of u times cosine of the angle between them. All right, now let's just do some algebra. If I were to subtract off the v squared on both sides, we get that they cancel out. I can do the same thing with the magnitudes of u squared. So those will also cancel out. So on the left-hand side, the only thing I have remaining is this negative 2 u dotted with v. And on the right-hand side, the only thing remaining is negative 2 times the magnitude of v times the magnitude of u times cosine of the angle between them. So if I divide by that negative 2, I get that u dotted with v is equal to the magnitude of u times the magnitude of v times cosine of the angle between them. And this is exactly the rule that we were trying to prove. All right. So we can use this form of the dot product to find the measure of an angle between two non-zero vectors. So the following equation emerges from this. All right, so here's the rule that we have. Cosine of our angle is equal to, we'll just divide both sides by the magnitude. U dotted with v divided by the magnitude of u times the magnitude of v. And since we're considering the smallest angle between the vectors, we're assuming that our angle is between 0 degrees and 180 degrees for degrees, or our angle is between 0 and pi radians. So the inverse cosine is unique over this range. So we're actually able to get the exact measure of the angle theta. So let's take a look at the example.